we've introduced the concept of switching in communication networks, and we've identified 3 different types of switching: circuit switching, and 2 forms of packet switching: datagram packet switching and virtual circuit packet switching. We want to just summarise on them and make sure it's clear on the differences between those 3 different types, and in particular see how packet switching works, and then we'll go through 1 or 2 short calculation type examples to show some performance characteristics. In summary, what do we know so far? Circuit switching, we establish a path from source to destination before we send data. We establish a circuit or a connection or a path. So before we send data, the source sends a message to the destination, and along the way the switches set up that connection, assuming there are enough resources. So in circuit switching, you set up a connection, you must have enough resources in the network to support that connection. If not, the connection will be rejected or blocked. It's the same as when you try and make a phone call. If the network is busy, because there are not enough resources to support your phone call, then your call is blocked. You cannot make the call. Circuit switching, once we set up the path, we transmit the data in a continuous manner. That is, there's no concept of packets. Because we have a dedicated path from source to destination, it's as if we have a link all the way. And if we have a link from A to B, we just transmit the data. Once we transmit the data, there's no processing in the switches in the middle. So there's very minimal or very small delay inside the switches once we've set up a path. We simply transmit a signal from the source and it flows through the switches until it reaches the destination. That's with circuit switching. With packet switching, we break the data into packets, into chunks. We attach headers, 2 different variations. With datagram packet switching, we have our data, we just send the packets. The source generates the packets and transmits them. And the switches in the network process those packets, and the packets contain headers, and at least in the headers it must contain the destination address, so that the switch knows it receives a packet destined to F. It must know which direction to send it to reach F, okay, because it must reach the destination. So with datagram packet switching, we divide our data into packets, send the packets one at a time from the source, and the switches in the network have the job of delivering those packets to the destination. They may take different paths. The switches don't worry about how it treated a previous packet. It treats packets independently. Simple, in that there's no need to do anything before you send the data. The source just sends the data. There's no concept of setting up a connection. Then the alternative, or the other form of packet switching, is virtual circuit packet switching. Here we try to pretend like we're doing circuit switching. The name virtual circuit. It's not a real circuit. We are still using packet switching. That is, we still have packets. We send 1 packet at a time. But we try to, before we send our data, we establish a path from source to destination. We're going to send all our packets belonging to this set of data along that same path. In that way, we know that the destination knows it's going to receive some data, it's prepared to receive the data, and the switches know that some data is going to flow through them. But still we use packets as opposed to setting up a physical path in circuit switching. We finished yesterday looking at some different examples where we looked at a switch sending on to the next switch where that link has a capacity of 10 units, 10 megabits per second, for example, or 10 packets per second, but 10 units. And we have nodes sending into those switches. If we're, depending upon the requirements of the source nodes, we have different impact depending upon which of the switching techniques we use. If we use circuit switching, the source nodes need to set up a connection before we send data, and that requires some reservation of resources. So if the the sending rate of the source nodes normally will vary. So in practice, for an application, it may not be fixed. So for the duration of the time I want to send data, the sending rate may vary between 0 and some upper value. Sometimes it may be fixed for some applications, but others you may send data and then not send anything. Or you may have a lot of data to send and then just a small amount of data to send. So the sending rate may vary. Let's say, for an example, for source 1, for source A, the rate that it wants to send varies between 1 and 2. B varies between 2 and 5. And C between 2 and 6. Just as an example. So when computer C wants to send its data, the maximum it wants to send out is 6, and the minimum is 2. It may range between there. And we cannot predict what it will be. If we use circuit switching, then let's say computer A comes along first, makes a reservation, so sends a request to set up a path. Then the switch looks at the resources available. Of course, in other parts of the network we have to do this as well, but focusing on this switch, it has a capacity of 10 units. A requires a maximum of 2. So we would reserve or allocate 2 units for circuit switching to A, 2 of the 10. And then if B comes along and makes a reservation, then we may reserve at the switch 5 units for B. And then C comes along and makes a reservation requesting 6 units because that's the maximum it wants to send. It may send less sometimes. If it requests 6 units, then it will be rejected. Capacity is 10, current reserved is 7. We cannot support another 6. So with circuit switching in this simple case, the request from C to set up a connection, if A and B have already set up a connection, would be rejected from this switch because there's not enough remaining. Okay? So we'd only use 7 out of the 10 in this case. So that can be inefficient because some of it's unused in terms of the capacity of this link. So with circuit switching, that's what may happen. What about with packet switching? I'm focusing first on datagram packet switching. We do not set up a connection, we just send our packets. And the rate at which A, B and C send their packets varies. Okay? Between 1 and 2 at A, between 2 and 5 or 2 and 6 at C. If they're all sending at the minimum rate at some point in time. Okay? So A is sending at 1, B at 2 and C at 2. Are sending packets into the switch, packets arrive, then everything should be okay in that the switch can send the packets out at the same rate. That is, sends at rate for 1 for A, B at 2 and C at 2. It will not send out any faster than what comes in. If you think of packets per second, if A is sending in 1 packet per second, the switch can send out a maximum of 10 packets per second. 1 of them is for A. Okay? 2 of them are B's packets and 2 are C's packets. Because you do not send out more than what comes in. So this is okay. That's if they were sending at the minimum rate. Of course, the rate at which they send varies over time. So at another time, maybe B is sending at its maximum rate. A is sending at 1, B at 5, C at 2. So still would be okay in this case. The amount coming in is 8 packets per second, for example. So the switch would send out 1 packet for A, 5 packets for B, and 2 for C every second. Of course, the problem arises when they start to send at higher rates. And let's say if they all send at their maximum rate, 2, 5 and 6, then the amount coming into the switch is a total of 13 packets per second. So the switch can only send out at 10 packets per second. Now, what the switch would normally do is, as the packets come in, then choose some of them descend out, 10 of them descend out. So how does it choose? That depends upon the setup of the switch and the network. But let's say it chooses, of those 10, so there's 13 coming in. Think of there's some queue or memory. The packets come in or put into the queue, and the switch transmits those packets. It can transmit, of the 13 that come in, 10 of them. Let's say 1 for A, 4 for B, and 5 for C. This split could change, but note that the total here is 10. We can only send 10 out. Which would mean A sends 2 packets in that time period. Only one of them comes out. That other packet is in the queue. A packet from source A. Similar, B sends 5 packets in, only 4 come out, another one is in the queue. And similar for C. So in this case, the input rate is larger than the output rate. As a result, some of those packets must be stored in the queue and be transmitted later, at some later time. This split here that I've chose, 1, 4, 5, is just an example. It could be different. Just the point is that it totals to 10. It could have been 2, 3, 5, or any other split. The point is that some packets will be queued there. If then in the next second, of course, there's another 13 packets coming in. Okay? There's already 3 in the queue. Another 13 come in. So what the switch does, it transmits 10 of them. Normally it would transmit the ones already in the queue, transmit these 3, but there's another 13 at the end. So it transmits these 3 plus another 7 of the 13 new ones that come in. Leaving how many in the queue? How many are in the queue after the next step? We've got 3 in the queue. Another 13 come in. We can only transmit 10. What's left over in the queue? Not 3. How many? Not 3. There are 3 currently in the queue, A, B and C. There's another, to keep it simple, every 1 second, what is the number of packets that come into to the switch and are stored in the queue. So 13. 13 new ones come in, 3 old ones in the queue. So in fact, inside the switch we have 16 packets, but we transmit 10 out. So in fact, we'd have 6 packets in the queue. Okay? And if we keep going like that, the queue will get longer and longer. The longer the queue, the larger the queuing delay on average for each packet. So the queuing delay would go up. Eventually the queue may fill up. If the queue fills up, then we have to start dropping packets. We lose packets, and that's bad for our applications. We need to retransmit and so on. So if the input rate exceeds the output rate for some long period of time, our queuing delay will keep going up, and eventually packets will be dropped. Okay, any questions on how that works? Yep. Okay, let's try and draw it. And it doesn't work exactly like this, but to keep it simple, I'm saying every 1 second we have some coming in and some going out. In the first 1 second, total coming in this case is 13. Okay, in the first 1 second, 13 come into the switch. Think of all 13 are stored in the queue. So all of them are in the queue there. But of those 13 in the queue at this point, 10 of them immediately transmitted. So there were 13 in there that came in, 10 were transmitted, leaving 3 say A, B, and C. 3 still waiting in the queue in the first iteration. Then in the next iteration, another 13 come in. So we have these 3 in the queue plus another 13. Let's say A, B, C. I don't know what they are, but there's 13 here and 3 already. So in fact there are 16 in the switch, but we can transmit 10 of them. So we transmit, say, the first 3 and the next 7. We have 16 in the queue, we have 10 we can transmit, we have this 6 remaining. 6 packets remaining in the queue in that case. And then in the next iteration, another 13 come in. There are 6 already in the queue. We transmit 10, there'll be 9 remaining, and so on. We'll keep increasing the queue size by 3 because 13 on in, 10 on output, there's 3 left over each time. So over time, the queue size will build up, packets will be delayed more because each packet that waits in the queue has some queuing delay. Eventually, if the queue fills up, no more packets can be put in the queue, then we'd have to start dropping the packets. Packets are lost. That's the worst case because all of them are sending as fast as possible. But remember, over time, the sending rate changes. So even though we have 6 packets in the queue now, maybe the sending rate has dropped on some of them. This has dropped, B has slowed down to 3, and C has slowed down to 4. Because the sending rate varies over time. Total coming in is 9. We have some in the queue. We have 9 coming in plus 6 in the queue, 15. We transmit 10 out, there's just 5 remaining in the queue. Another 9 come in, 9 plus 5 is 14. 10 go out, 4 remaining in the queue. The queue is going down in size because our input rate is less than the output. So over time, as the sending rate or the input varies, our queue size may increase and decrease. Hopefully, over a long period of time, it will stay at a small size. It will not get too large, depending upon how much this varies. Any questions on that basics of packet switching or how the queuing works? Same applies for virtual circuit packet switching. It's for both of those switching techniques. The benefit is that we can allow for dynamic sending rates. With our circuit switching, we could only support 2 of them because we had to allocate and reserve 2 and 5, a total of 7. But with packet switching, we can allow all 3 of them to be sending. So A, B, and C are all sending their data through the network. The problem is that sometimes if they all send at their maximum rate, the queue delay goes up. So there's extra queuing delay. But if they are varying their rates, sometimes that queue delay will go down to 0 again. It won't be a problem. So we can allow for dynamic sending rates from the sources. It caters for the dynamics much better than circuit switching. With circuit switching, if we have dynamic sending rates, that is changing sending rates, the network can be very inefficient. We waste a lot of the resources. Okay? So that's the advantage of packet switching versus circuit switching. Today, in most of our internet applications, we have dynamic sending rates. We don't always send data from our computer at the same speed for all day, 24 hours a day. Over a period of 1 minute, if you look at the sending rate, the number of packets you send out of your computer, it will change. Sometimes you're not sending anything, sometimes you're sending a lot. So with many internet applications, the sending rate of our sources changes over time, and hence packet switching is better suited than circuit switching and is used in the internet today. Any questions before we look at some performance comparison of the two? This diagram tries to summarize the timing of the sending of data and the call setup. We'll go through it in a moment. It's not this simple in real life. Packets don't come in all in 1 second and then transmit them. It's varying over time, but the similar concept. In real life, packets arriving at different times, at random times. But that demonstrates the concept. This diagram shows circuit switching, virtual circuit packet switching, and datagram packet switching, our 3 techniques. And it shows the timing diagram for an example where we have 3 links. So a network with 3 links between source and destination. We'll go through it, we'll come back to it in a moment, but we see the basic approach. In circuit switching, we send some initial request message. Here it's called a call request signal. This is to set up the circuit. Each circuit switch processes and sends on to the next one, so it checks whether we have enough resources. If so, send it on. If this one has enough resources, send it on. And then everything's okay, we send back a response. Here, we see that we send back the response. There's no processing at the intermediate nodes because the circuit is already set up. It's as if we have a link all the way from node 1 to node 4. And then we transmit the data. So it's showing transmission delay and propagation delay. Yeah. Similar to how we've drawn diagrams in other topics. And then the data is received at this time. Virtual circuit packet switching, we set up a connection and we send back some response, and then we send the data but as packets. And with datagram packet switching, there's no connection set up, we just send the data as packets. We'll come back to that in a moment. Before we go through it in more detail, let's look at the impact of packet size on when we use packet switching, either datagram or virtual circuit packet switching, the impact of packet size on performance. In particular, on the time it takes to deliver the data to the other side. Here we have an example. The source is X as a link to A link to B, and then to Y. So that's our path. Our packets are going to go from X to A via X to Y via A and B. And this is a summary or a simplification of our message sequence diagram. In the first diagram on the left, it assumes that the data that source X has to send is sent in one packet. That's what this shows. We take the data and transmit it in a single packet. Let's put some numbers to it. Let's say the total data, the real data, is 1,000 bytes, 1,000 units. Or it takes 1,000 units of time to transmit. Whether we look at bytes or transmission time, it doesn't matter. And in the first case, on the left, we say that a packet contains 100 of header and then 1,000 of data. That is, each packet has a maximum size that it can fit 1,000 bytes of data in it. Okay? Which means in this case we can fit all of our data in one packet. So what we do, computer X transmits one packet to A transmits that packet to B, and B transmits it to Y. And that's what this diagram is showing. That is, it doesn't show the vertical lines nor the propagation delay, but it shows the transmission time. That is, we transmit the first packet, there would be some propagation delay. It's not shown in here, so it's very small. With transmission time. And with packet switching, the node must receive the entire packet before it transmits to the next node. So we start transmitting the first packet from X to A, transmitted across the link, and we're transmitting. There's some small propagation delay. A starts receiving the first packet, receiving. At this point in time, A has received the entire packet, and now maybe there's some small processing delay, and then transmits that packet to B. And that packet's going to propagate across the link, received by B. When B's received the entire packet, it looks at the header, sees where it needs to send it, and realizes it needs to send to Y. And then the data at this point in time is received by Y. So that's what this diagram is showing, except it doesn't give any propagation delay. Assume the propagation delay is very small here. If the time to transmit the data is 1,000 time units, 1,000 milliseconds, microseconds, and header is 100, if we start at time 0, what is this time? The time at which we've finished transmitting the first packet. What's the number? If we start transmitting at time 0, the first packet, at what time have we finished transmitting the first packet? 1,100. It's 1,000 of data plus the 100 of header. Easy. Now, assuming no propagation delay, so if we finish transmitting here, we'd receive it at the same time. In our other examples, we've had some small propagation delay, like let's say if there's a propagation delay of 1, then we'd receive it at 1101. But to keep things simple, let's say that the propagation delay is 0. So we'd receive that first packet at 1100. And then we immediately start transmitting that packet from A to B. So node or switch A starts transmitting. How long does it take to transmit? 1,100. Therefore, we finish transmitting at 2,200. And here would be 2,200. And then another 1,100. We'd receive at time 3,300. Again, 0 processing and queuing delay, 0 propagation delay in this example. So in the first case, it takes, if we put numbers to this diagram, it takes 3,300 time units to deliver the data from A to B, from X to Y in our case. Any questions on how those numbers were arrived at? How you would do that in the exam? It's just looking at transmission delay. We transmit one packet. Once we receive it, we can send it across the next link, and so on. Let's draw it again over here. X, A, B and Y. Let's try a different scenario where the packet size, same header size, 100, but the data, the payload, is now 500. So each packet contains a 100 unit header plus 500 of payload. We still have 1,000 bytes of real data to send. So we need to divide it into 2 packets. Okay? So packet 1 and then packet 2. And that's what's shown in the next diagram here. We'll do it here. We transmit packet 1 from X, and then it immediately transmits packet 2 from the source node. We start transmitting at time 0. What time do we finish transmitting packet 1? 600, 100 plus 500, so 600. And packet 2, another 600, so 1,200. Okay. We transmit 2 packets. It's slightly longer than before because we have 2 headers. With 2 packets, each one needs its own header. Following the same approach as what we did, packet 1 arrives at A at time 600. That is 0 propagation delay. Packet 1 arrives at switch A. Switch A looks at the header, realises they need to send this packet on the next link to B, and starts sending that packet to B. And note what's happening here. Switch A has 2 links. One is a link to X in this direction, and one is a link to B. And at this point in time, it is receiving packet 2. It's receiving packet 2 from X, and at the same time transmitting packet 1 to B. Because it has 2 links, it can be doing both at the same time. So receiving one packet and transmitting the previous packet across the next link. So let's label 1 and 2. Similar, packet 2 would be received here and then transmitted to B. And of course, the 600 to transmit, so this would be 1,200, 1,800 this time. Similar, B is receiving packet 1. At this point in time, it's fully received packet 1 and then can transmit that packet onto Y. And then at the same time that B is receiving packet 2, it's transmitting packet 1 and can then transmit packet 2. And if you follow the timing, this would be, what, 2,400. And we'd receive all of the data, it carried in 2 packets at time 2,400. When we used a large packet, we took longer time, 3,300 units to carry the same data from X to Y. Using smaller packets, we got a shorter time, which is different from what we've normally thought about, because normally we think the smaller packet, the header contributes more overhead, and it does. Why have we gained in this case? Why have we got a short time in this case compared to the first one? Normally we think with a small packet there'll be a larger overhead because of the header, and that would be less efficient, which is true. In this case we can send and receive at the same time. Because we've got 2 packets, we've got something happening in parallel. In particular, a switch is receiving a packet and at the same time transmitting the previous packet it received. We don't have to wait. Because we've got 2 packets, we can be receiving one and transmitting the previous one across the next link. So we save some time here. And same at this point. So using multiple packets helps in this case. I won't go through the calculations, but the next two diagrams show similar scenarios. I'll write down the numbers. The third one, if we have a packet of 100 bytes of header, so the header is still fixed, and 200 of data, which means we have 5 packets in the third case. 5 packets transmitted. You can calculate the total time. I think it's 2,100. And the fourth case, we have a smaller packet again, 100 bytes of header plus 100 bytes of payload, 10 packets. The total time, 2,400. So we see the packet size impacts upon the total time to deliver the traffic across the network. The best one in this example is the third one, is that it takes the least amount of time. It's related to the number of packets we have. Can we transmit them in parallel? That is, be receiving a packet and at the same time transmitting a packet, but still the header has some impact. In the fourth case, we have smaller packets, but the header contributes a lot because we have 10 packets, 10 headers. Here we have 5 packets, just 5 headers. So the extra header that we need to transmit contributes more to the delay, and we get slightly longer in the fourth case, 2,400 versus 2,100. So there's a trade-off here. It's no one best. Well, you need to consider both the number of packets, the number of links we have. In this example, there were 3 links, and the header size relative to the data. If you have more links, do you want more packets or less? To be efficient, to save on time, if you have more links to send across, then you would gain more by having more packets, by breaking it into smaller packets, which is what we see here. If we have a large packet, when we have 3 links, we don't get a chance to send in parallel or to receive and transmit at the same time. But with 2 packets, we do get that chance. So it depends upon the number of links, the number of packets, and the header size. Any questions on the impact of packet size on, this is just for packet switching delay. You may see past exam or quiz questions which calculate the total time. Given a number of links, maybe instead of 3 links, 4 links, if you know the transmission and propagation time, you can calculate, given the packet size, how long it takes to deliver. See some pattern here? That is, in terms of transmission, the source transmits the 5, and the extra time is that because these 4 are happening at the same time, then we have this 1 extra off the next link and then 1 across the next link. So in fact, there were 5 plus 2 transmissions in this case. 5 plus 2, 7 times by the packet size, 7 times 300, which was 2,100. In the last case, the source transmits 10, and while that's happening, these 9 are being transmitted from A. So there's this extra time for A to transmit the 10th one to B, and similar the 10th one from B to Y. So you can count there are 12 transmissions from the start time to the finish time. 12 times our packet size of 200, 2,400 is the total time. So you can calculate, if I give a question, what if there are 1,000 packets in some scenario? You don't draw the diagram, but you need to think about the general structure and how to calculate that. Or 1,000,000 packets. another aspect with what we just showed there was the data delivery and packet switching. If we were using datagram packet switching, that's the only delay. That is this case. This is datagram packet switching. In this diagram, we have circuit switching on the left, virtual circuit packet switching in the middle, and datagram packet switching on the right. With datagram packet switching, there's no setup phase. So the delay to deliver the data from when I have data to send depends simply upon what we just calculated, the number of links, the packet size, the header size, and so on. So that's an example with datagram packet switching. But with the other two approaches, we need to first set up the connection. So let's say I open my application and I press start to start sending the data at this time. If we're using circuit switching, we need to send some special message to request to set up the connection. Here it's called a call request signal. A response needs to come back saying it's okay, and then we transmit the data. The data is received at this time. So the delay from when I press start on my application until node 4 has received all of the data is from here to here. Similar with virtual circuit packet switching. When I press start, I must set up the connection, then send the data, but this time as packets. With datagram packet switching, I press start, just send the packets. There's no setup phase. So comparing them in terms of the delay, it depends upon how long it takes to set up the connection as to which one's best. Comparing datagram to virtual circuit packet switching, under the same conditions, datagram packet switching will always be shorter than virtual circuit packet switching because this is the time to transmit the packets, which is the same as this time. Virtual circuit packet switching also has the call setup delay. So when I press start on my application, starts here, it takes some time before the data is delivered. In the middle case, it's the setup plus the data delivery. In the right case, it's just the data delivery. So the timing to complete that data transfer depends upon not just the packet sizes of the links, but also the setup delay. For the two cases which have setup, there's some extra time to set up that connection or circuit. And they are generally not suited for when we have a small amount of data to send. Because if the data is small, we still need to do the setup, which takes the time to send a packet there and get it back, or a message and get it back. If we only have one packet of data to send, we set up a connection, send one packet. So when we have a small amount of data to send, using a connection setup can be inefficient. It takes too much time. When we have a lot of data to send, if this data was very large and many packets, then even though we need to set up the connection, it incurs some delay. It's usually very small compared to the data transfer. So setting up a connection is inefficient when we have a small amounts of data to send. For example, request a web page. Send a small packet to the server and get one response. Then to set up a connection just to do that can be inefficient sometimes, wasteful. Datagram packet switching may be better in that case. The last thing we should point out here is the data transfer for circuit switching. We don't use packets. Once we've set up the connection, we have our, let's say, 1,000 bytes of data. We simply transmit that and it propagates across the first link, through the first switch because it's already established a path, across the next link, and through the second switch, and then across the third link and is received. With circuit switching, we don't have to wait or process anything at the intermediate switches. It just passes straight through those switches. So it's as if we have a link from source node through to destination node. The delay simply depends upon the transmission plus propagation across all of those links. But with packet switching, send one packet, wait for it to be received, then transmit it across the next link. So we have this extra delay here. Circuit switching is faster to deliver the data compared to packet switching. And that brings us to the end of this topic on switching. The next slide gives some more detailed comparison, but I think we've covered the main things that we want to compare them, the three different switching techniques. Before we move on, any questions to finish on switching? Yep. The one on the right is datagram packet switching. In datagram packet switching, there's no connection set up, no circuit set up. You just send your datagrams or your packets. The middle one is the virtual circuit packet switching. Before we send our data, the packets, we send a special message to set up the connection and then get a response. Any other questions? Yep.
What is the advantage of virtual circuit over Datagram?
So what is the advantage of virtual circuit packet switching versus datagram packet switching? Well, we can see one disadvantage of virtual circuit packet switching. It takes longer to set up the connection. But we know when we use virtual circuit packet switching, once we set up the connection, all the packets follow that same path. There's one advantage. That is, in datagram packet switching, the packets may go any path, in theory. They may take different paths to the destination. Another thing is that by setting up a connection, we have informed the receiver that they're about to receive packets. That can be useful because you tell the receiver, I'm about to send you some packets, and it prepares, in terms of it prepares buffer space or memory space in anticipation of the packets being received, so it can be prepared for the packet reception. That's a small advantage, whereas with datagram packet switching, the receiver doesn't know about anything coming in advance, it just receives the packets. With virtual circuit packet switching, we can do similar to circuit switching, and we can reserve some resources. We could, in this call request packet, tell the switch, we're about to send 2 megabits per second of packets along this path. Please reserve some space in the switch. So we can still reserve resources in virtual circuit packet switching. So we can get similar benefits to circuit switching. However, in practice, we can reserve resources, but sometimes it's not 100% guaranteed. We still may have packets arriving at a switch, and some packets may be queued. So there still may be queuing delays, meaning the delay cannot be guaranteed. With circuit switching, the delay can be effectively guaranteed for our data. With packet switching, the delay may vary because of the queuing delay. Another advantage of datagram packet switching, it's simple. You just send packets. There's no difficulty in, at least for the sender and receiver. And there's no need to have this extra step of setting up a connection. Telephone networks based on circuit switching. Some old data networks use circuit switching. Some other, maybe a little bit more recent, 10, 20 years ago, data networks use virtual circuit packet switching, and there's still some around. So there's some technologies use virtual circuit packet switching. The internet is based upon datagram packet switching. Okay? The internet protocol uses datagram packet switching. It chooses the simplest of the approaches, even though it may not be the best performing sometimes, because we cannot guarantee performance, it's the simplest. That table just summarises some of the details or some of the trade-offs between them. In the last 20 minutes, what I'll do is just introduce the next topic. And we mentioned this before, with a network, there's two problems. Getting the data from A to B, from source to destination, so we looked at the switching techniques, but the first problem really is which path to take from the source to destination. And that's what routing's about, finding the best path from source to destination. We're going to look at routing, what is routing, how can we perform routing. We'll look at some different approaches for routing, or some routing strategies, and briefly at the end mention some real protocols or some algorithms that are used for routing, especially in the internet. We're going to focus on, in the examples, routing in packet switch networks, because the internet uses datagram packet switching, but routing applies for all of those switch networks. In circuit switch networks, we need to find the best path from source to destination before we set up a connection. So in all of them we use routing, but most of our examples now will look at packet switch networks. Routing, the problem is simple. We have our example network, we want to get from A to F, which path do we take? Any suggestions? Which path to get from A to F? (476). Okay, someone's chosen 476. Anyone got a better one? 456. So there are multiple paths. That's the first. That's normally in a switch network we have multiple paths from a source to destination. The challenge is finding which, or choosing a path to take, and we'd like to choose the best path. In this case, do you think 476 is better than 412356? Possibly it is. Why are you saying yes? Why do you think it's better? It's shorter, okay? The number of links that we traverse is one thing that we may define as being better. Choose the path which is shortest from source to destination. It doesn't have to be that. There may be other factors that determine which one's best. It may not be the shortest in terms of the number of links. An example is you want to drive into the city. Okay, here you are, Bangkadi, you want to drive into the centre of Bangkok. Which path do you take? Okay, there are many different roads. Okay, you can drive via different directions. You need to choose a path. How do you choose a path? Less traffic. Okay, so there's one. Choose the path and let's record. Less traffic. Anything else? Shortest distance, okay. So there's another approach. Anything else? Anyone else may choose some other factors you may consider in choosing lowest cost. Maybe you don't want to pay the tollway fee. lowest financial cost in that case. So there are different ways that we can define what is the best path, and it would depend upon what your requirements are. We would call these routing metrics. That is the way that we measure the cost of using some path. So, generally, they are measuring the cost of a path. Not a financial cost, but a generic cost. For example, the cost may be related to traffic. The less traffic, the lower the cost of using that path. Or if the cost is related to distance, the lower the distance, the lower the cost of using that path. Or it may be financial costs. So we use a general term of cost to mean any of these or any metric. And normally what we do is once we can assign a cost to the path, whether I choose amount of traffic, distance, or financial cost, then I apply some algorithm that calculates the path which is the least cost. So we come up with, which will define least cost routing. For example, in our network, if we assign costs to links, let's say we use the metric of the number of hops. A hop is one link in this case. This is one hop, another, and here. So we can say this path, 476, from A to F, there are 1, 2, 3, 4 links, or 4 hops. We could say that this link has a cost of 1. It's one hop, 1, 1, 1. Each link is assigned a cost of 1, because each link corresponds to one hop. And then we'd apply some algorithm of all these paths, find the one with the least cost. And I think you'll find this one has the least cost, and this one as well, because the least number of links. Instead of looking at the number of links or the number of hops, we could say there's some financial cost of sending data across each link. This is someone's network. We need to pay to use their network and to send data across the links. There may be a financial cost of using this link, 1 baht per minute or something. And another financial cost that may be more expensive to use this link. So we'd assign some generic cost based upon the financial cost of using a link to all the links, and it then use the same algorithm to find the path with the least cost. And that will determine. So we can have any or many types of cost metrics, ways for measuring the cost. It doesn't have to be the shortest in terms of number of links. Coming back to driving into Bangkok. How do you... Someone said less traffic. How do you know how much traffic is on the roads between here and Bangkok? All right, but experience, okay, so past experience, okay, that's fine. So how do we, the question is, I'm here at Bangkadi and I need to make the decision now to drive in and choose a path. My metric is choose the path with the least traffic. How do I know which one has the least traffic? Okay, past experience. If I've driven there before, I know some intersections may be busier than others. Okay, anything else?
Instinct.
What's instinct? I think you cannot use that standing here and say, I can use experience, but I think instinct is related to that in that case. What else?
Google Maps.
Google Maps. What does that tell you? Okay, some online systems may tell you the real-time traffic. So some, what do we call it? Some traffic mapping or some traffic mapping software or traffic real-time traffic measure, say Google, or what's the old style? Radio. Okay. Sometimes on radio or on TV they say that there's some accident at this intersection, or the traffic's bad here. There's a helicopter that flies around and keeps track. So there's some updates. Past experience, maybe your experience, or maybe your friend has driven there in the last 1 hour and told you on the phone what the current status was. So we need some ways to collect the information to know about the traffic. So we have a set of paths. We need to assign costs to those links. In this case, what we're doing is saying, okay, each portion of the road, this path, then we expect the traffic will be high on this one, low on this one. Well, where do we get that information from? Past experience, radio, Google, and so on. So we need some ways to collect the information. Okay, of these, past experience, maybe you drove there yesterday. Okay, that's one thing. So yesterday's experience. The radio gives an update every, let's say, every 4 hours. Lunchtime, and then in the afternoon they give an update. Okay, the current traffic conditions are this. And Google has some cameras throughout the city, and they give, and some feed from the traffic information centre, and they give update on the Google Maps every 1 hour. Which one is better? The shorter time. The one with the more regular updates is going to give you a more accurate picture of what the current traffic is in the network. I need to drive now. If I use information from yesterday's experience, in that 24 hours, the traffic may have changed. There may have been an accident at one intersection in the last 12 hours, which means the traffic has slowed down. So the rate at which the information is updated is important. The higher the rate it's updated, the more accurate my picture of the network is. And therefore, it's more likely I'll choose the best path. And I will not make a mistake and choose a path and end up getting stuck in traffic. So the update interval is important. How often is the information updated? I think that covers, we'll see them on the slide in a moment, those things that impact upon routing. We'll see a couple of others. So, we have a problem. What path or route? Routing is about finding a path or a route. We use those words to mean the same in this course. What path or route should be taken from source to destination? Well, the answer is simple, choose the best path. But the question then is, well, what do we mean by best? Well, we have different metrics to define best. It depends upon the requirements. We'll look at them in a moment. Note, in our examples, we have a small network. In real networks, there may be hundreds of nodes, hundreds of thousands of nodes in the internet, and hence many possible paths. It can be quite complex for finding which one's the best. You can't just look at a picture of the network and see. You need some computer software to calculate for you, and we'll see some algorithms to do that. Routing is needed in all the switched networks. We will just use packet switch as an example. So, actually we'll come back to this one, I think. Let's go through some terminology first. We talk about a link now. A link is a connection between two nodes in the network. A path is a way between two nodes, so via one or more links. So in this network, there are 3 links. A link from A to B is here. A path from X to Y is via A and B. So we have links and paths. A hop is to traverse a link. We travel 1 hop, 2 hops, 3 hops. So really, the hops is the number of links we traverse. We'll often talk about hops as a metric. A neighbour is a node at the other end of a link. So the neighbour of X is A. The neighbours of A are X and B. Okay, so nodes have neighbours or direct neighbours. In a general cost, this is not a financial cost, but a general cost is a value assigned to a link to indicate the cost of using that link. So if we assign distance, if we use distance as the cost metric, and we assign some value, if the distance from X to A is 2 kilometres, and from A to B is 3 kilometres, and B to Y is 4 kilometres, then the cost assigned to this link would be 2, 3 and 4. Simple. Okay, so we assign some generic cost to our links depending upon what metric we're going to use. If the cost of using this, if it was 2 kilometres but the cost of using the link was 100 baht per time period, if this was 150 and this was 200 baht, then depending upon what cost metric do we use financial cost or distance, indicates what value we assign here. So a link may have different measures here, financial cost, distance, amount of traffic. We choose one of them or a combination of them to determine the generic cost assigned to a link. Topology means the arrangement of nodes and links in a network. Just some terminology to set us up. So this is one topology of a network. X is connected to A to B, B to Y. This is another network with a different topology. So we have the same number of nodes, but a different arrangement of the links between those nodes. So this is one topology, this is another topology. And this is another topology, a very simple one. But just the arrangement of nodes and links is what the topology refers to. What we do in routing is we assign costs to links, and given some source and destination, we use least cost routing, which chooses a path from source to destination with the least total cost. That's the general least cost routing. Find a route or a path with the least cost, where the cost depends upon the metric we choose. Well, I think we don't need to go through this. We'll use this example later. We define the terminology. This is one topology of the network. These are nodes, links, and the numbers assigned here are costs, just for this example. So the cost of sending data from 1 to 4 is 1 unit, whatever the metric we use. And note that the cost of sending in opposite directions may differ. The cost of sending from 1 to 4 is 1, but from sending from 4 back to 1 is 7 units. So it's possible that the costs in different directions may differ. Maybe the data rates differ in each direction. Your ADSL connection, your upload rate is lower than your download rate. They have different data rates across that link. So the costs may differ in general. They may be the same, they may be different. So an example of a network, and we'll use that in the rest of this lecture. I just want to summarise what we talked about with our driving into Bangkok example, and then we'll finish. So some of the questions we need to answer are: what performance criteria are used to select a path? What cost metrics are available? Okay. We've come up with some for driving, and similar we can think of some for a network, number of hops. When do we select a path? Let's come back to our driving example. Let's say I select a path to drive into Bangkok, and based on some criteria, and I use that path to drive in today, and I use it for the next year, that same path. So I select it at the start of the year, and I'll use the same path for the duration of the year. And then the next year I will calculate again what is the best path and maybe update my path. Another approach is every day. Every day I need to drive in, I select the path, take that path, and tomorrow it may be a different path. So when do you select the path is important, because the more often you select it, the more accurate it will be. More likely you'll get the best path. But when it comes to computer networks, it takes some overhead to select the path. So it takes some effort to select the path. So the more often we do it, the more overhead or effort involved. So there'll be some trade-off there. Who selects the path? We'll not go through that now. We'll see an example later with that one. Which nodes provide information about the network status? Coming back to our traffic one, we needed to know something about the traffic. Who provides that information? That's important. In a network, a communications network, that information is about the topology, the cost of the links, and the current usage of links. So who provides that information is important, because it will impact on how up-to-date the information is and how much overhead involved in providing that information. And how often is it updated? 1 hour, 4 hours, every day. Do we get an update of the network status on a regular basis? That's good, because I'll choose better paths, but it's bad because, again, there's some overhead of collecting that information. Somehow my computer needs to know about the links throughout the internet if I want to choose a path. So it takes some effort or some overhead of collecting that information. So the more often you update, more chance you'll choose a good path, but the more overhead involved. Next week we'll go through how those questions, or different ways to answer those questions in routing in switch networks. I think for today we'll finish there. We'll go through routing in detail next week. Any questions to finish up for today? Routing is simple. Well, the concept of routing is simple. Maybe there'll be a quiz that's not available yet, but there'll be a quiz on switching with some simple multiple choice questions and 1 or 2 calculation questions on switching, which will give you practice. The last few slides we had on switching